Thank you everyone for attending our talk about ChaosDB, an account takeover vulnerability we found in Azure's most popular database solution, Cosmos DB. So just a quick who are we before we begin. My name is Sagi, and here with me is Neil.
Hey.
We are both security researchers from Wiz Research Team, and our team vision is to uncover new attack vectors in the cloud. We also presented in the last Black Hat and DEF CON events, and these are the talks that we gave. Our team does mostly cloud security research, and we publish our findings on our blog. Here are some of our most recent publications. Note that we are also planning to disclose more vulnerabilities soon, so stay tuned. Okay, so in August 2021, we reported Microsoft a cross-account vulnerability that we found in Azure Cosmos DB. Exploiting this vulnerability effectively allows any attacker to fully compromise Cosmos DB databases of other customers. This vulnerability got a lot of attention, and today, for the very first time, we are going to reveal all of the technical information behind this vulnerability, including how we even managed to get access to some Azure internal infrastructure. Before we dive into the technical details, let's go over the agenda for today. We will first talk about what is Cosmos DB and why we decided to research it specifically. We will then walk you through the technical details of the first two bugs that we found in this service, and then we will uncover some new information about an Azure internal component called the WireServer. With this new knowledge in mind, we will discuss the technical details of the third bug and how we chained all of the bugs together for a full account takeover vulnerability. We will then show you a demonstration of the full exploit, from unauthenticated attacker to a full database compromise. We will finish with a summary regarding everything that we've learned during this research. Hopefully, by the end of this talk, you will have a better understanding of Azure architecture in general and Cosmos DB specifically. You will also understand how we exploited multiple flaws in this architecture and chained them together for an account takeover vulnerability. Let's talk about what is Cosmos DB and our motivation for this research. For those of you who are not familiar with Cosmos DB, it is a managed database solution offered by Azure. This means that if you are an Azure customer and you need a database for your application, you will most likely use Cosmos DB. It turns out that this service is very popular among Azure customers. Let's have a look on this screenshot taken from Microsoft website, and you can see there are some very big names that are using Cosmos DB. Being a popular database solution, this makes Cosmos DB the holy grail for attackers. Everything an attacker wants from your organization is usually stored in a database, and for this reason, we thought that if we will find a vulnerability in that service, it will have a lot of impact. But if we are being completely honest, we didn't even intend to find a vulnerability in Cosmos DB. We were actually looking for common misconfigurations that customers can make when they set up their Cosmos DB account. But you know, one thing led to another, and here we are. So, as I mentioned before, at this point, we are not looking for vulnerabilities. We are simply scanning the features that this service has to offer to see what can be misconfigured. Then we noticed that Cosmos DB comes bundled with another product called Jupyter Notebook. For those of you who don't know what Jupyter Notebook is, it looks something like this. In short, Jupyter Notebook is a web application that lets you represent your data in cool ways using code. Cosmos DB users use these Jupyter Notebooks to view and analyze their data. Because we were already familiar with Jupyter Notebook, we knew that it lets its user execute arbitrary code in different programming languages. This raised multiple questions for us, like who owns this machine? Is this machine shared across users? And what resources can it access? So let's talk about the first bug that we found. We started digging into the Jupyter Notebook feature, and we quickly found out that we are running inside a Docker container using a low-privileged user named Cosmos User. You can see in that picture that this user has the UID of 9000 and GID of 9000. The service even offers an embedded web terminal, which is much more convenient, but we're still running as this unprivileged user, Cosmos User. Unfortunately, this user does not have root privileges and is not in the sudoers group. So we only performed some basic recon using this user, but there were still a lot of things that we wanted to access but couldn't. Then we wondered, how hard would it be to root this machine? After clicking on enough buttons in the web interface, we found a way to escalate our privileges. To our surprise, any code that runs in the C# programming language is actually executed with root privileges. This happens because behind the scenes, every programming language has its own host process, and for some unknown reason, the host process for the C# programming language specifically is actually running with root privileges. This means that all we had to do in order to elevate our privileges to root is to execute these 5 lines of codes in the C# notebook, and we get root. So let's quickly view a demo video of how we exploited this misconfiguration to obtain root privileges. What you can now see on screen is me opening the embedded web terminal and issuing the ID command to verify that I'm running as Cosmos user. We will also view the content of the etc password file to verify that our malicious entry is not there yet. Now, I execute the same ID command, but this time using the Python 3 notebook. And you can see that we are still running as the Cosmos user. Now, all I have to do in order to elevate my privileges is actually to switch the programming language from Python 3 to C#. Any code that will run in the C# notebook will actually be executed with root privileges. So our local privilege escalation payload edits the etc password file and append an entry there for the root number 2 user, which will have the UID of 0 and GID of 0, effectively granting us root privileges. Finally, what we have to do is to actually switch user to the root number 2 user in order to achieve our root privileges. And as you can see, once we finish doing that, we have root. Okay, so we are now done with bug number 1. Let's continue to the next one. So we now have root privileges on the machine. Let's try to answer some of our unanswered questions from earlier by performing a more extensive recon. We issue the iptables command to view local firewall rules in order to see which network resources we can access and which we shouldn't. You can see there that there are a couple of interesting rules here, so let's talk about them. First, there's this rule that prevents us from accessing the metadata service, also known as IMDS. The IMDS is a service that you can query using HTTP to view metadata information regarding your VM instance. For some reason, the developers of the service do not want us to access it. There's also this rule that prevents us from accessing the 10.0.0/16 subnet, and at this point, we do not know what this subnet is. The only thing that we know about it is that this is a subnet of internal IP addresses and that we shouldn't be able to access it. Finally, there's this rule that prevents us from accessing this IP address. Once again, we are not familiar with this IP address, and we don't know what its purpose and why we shouldn't be able to access it. But the good thing is that we are actually running with root privileges, and these are local firewall rules that were configured using iptables. This means that there is nothing that prevents us from removing these rules. As you can see in this picture, we simply issued the iptables-f command to remove the local firewall rules. These rules were not meant to protect from an attacker with root access. A safer approach would be to enforce these rules outside of the container. As an attacker, this makes me excited. We just removed the one thing that prevented us from accessing these network resources. And we know for a fact that the developer of this feature explicitly tried to prevent us from accessing it. So we removed the local firewall rules. This means that we can now access the IMDS. Given we are not supposed to access it, the only reasonable thing is to try and see why. You can now see on screen the answer that we got from the IMDS, and there are a couple of interesting things here. The first thing is that our Azure environment is set to Azure Public Cloud, and our subscription ID is not a subscription ID that we own. This may indicate that we are running in some sort of a shared environment, and that we are not the one paying for this virtual machine. Another interesting thing here is that our OS type is set to Windows. This is strange, we are obviously running Linux command in a Linux terminal. Why is it set to Windows? After exploring our environment a bit more, we concluded that we are actually querying our host machine metadata service and not the metadata service of our container. The last thing that you cannot see in this picture is that according to the IMDS, we also have an IP address in the 10.0.0/16 subnet. Just to remind you, this is the same subnet that we are not supposed to access according to the firewall rules. Okay, let's do a quick recap about everything that we achieved so far. We set up a Jupyter Notebook container for our Cosmos DB account, and we escalated our privilege there from Cosmos user to root. The next thing that we did was a basic recon. We found out that we can remove the local firewall rules and therefore gained unrestricted network access inside our environment. After that, we queried the metadata service and found out that we are not the one hosting this virtual machine, and it is probably hosted by Azure, perhaps in a shared environment. I will now hand it over to Nir to continue explaining about our recon efforts.
Thank you, Sagi. Let's continue the network recon. If we'll have another look at the machine IP table rules, there's that mysterious IP address. What is this IP address? When we searched this IP address on Google, we found this MSDN article. According to this article, this is a virtual IP address that exists on every Azure virtual machine, and it has a name, the WireServer. What does the Microsoft documentation say about this mysterious endpoint called the WireServer? First, we know it's a server that is accessible in HTTP, and that this server manages the extensions of every Azure virtual machine. Extensions are just software applications that Azure manages. They can be first-party software, like Azure's Log Analytics agent, or third-party software that Azure supports, for example, Datadog. When a customer chooses to install an extension via the Azure portal, the WireServer instructs the virtual machine's agent to install the extension, supplying the appropriate configuration. That configuration may even include sensitive information, and any extension information that we can extract from the WireServer will help us to better understand the underlying virtual machine and the environment we are running in. But, after looking at all the documentation that Microsoft has to offer about the WireServer, what is most evident is that this server has little to no documentation. But there's a silver lining. The WireServer has two clients designed to install and configure extensions based on the information fetched from this server, the Linux and Windows virtual machine agents, that come pre-installed on all Azure virtual machines. The Linux agent, also known as the WA agent or the WA Linux agent, is an open source project hosted on GitHub. Maybe by reading the source code of the Linux agent, we'll be able to learn something about the WireServer's functionalities. It's also worth mentioning that some of our research regarding the WireServer is based on the work of another security researcher, Paul Litvak from Intezer. Paul already did some high-quality research on this topic and detailed it in a great blog post. To recap, you can think about the WireServer as the backend of the WA agent, the Azure Linux virtual machine agent. It is used to supply any information that the agent needs to function properly. With that in mind, let's examine how the WA agent gets its extension information from the WireServer. The first thing the agent needs to do before fetching any configurations, let alone the extension configuration, is to download the machine's goal state. The goal state is, among other things, a phone book of endpoints responsible for different kind of information. It contains a list of endpoints that the agent needs to contact to fetch different configuration settings. Note that you can download any Azure Virtual Machine goal state by executing the following curl command. Using this command, you can retrieve all the configuration endpoints specific for your virtual machine. And here you can see the goal state we fetched executing the curl command on our own Linux virtual machine we set up for testing. Here you can see that it contains a bunch of different URLs, but the URL we care about is the extension configuration URL, which holds all the information about the virtual machine extensions. We were initially forbidden from accessing the WireServer because of the local firewall rules, but now we can start fetching information. Let's try to get the information of the underlying machine's extension by executing the same curl command on the Jupyter Notebook container, and get the underlying virtual machine goal state, including its extension configuration URL. Now, after getting back our extension configuration URL, let's try to access it as well. Now we can fetch extension information from the extension configuration endpoint. Here's an example of the extension configuration from a Linux-based virtual machine. In this case, the Linux diagnostic extension. The extension configuration section has two main parts. There's the public settings section, which is now highlighted in red, that contains public data without any sensitive information. And there's the protected settings section, which is usually encrypted, and therefore we suspect that it might contain sensitive information. This is the Linux diagnostic base64 encoded encrypted protected settings. Now, with that in mind, let's examine the Jupyter Notebook extensions. Remember that although we are running inside of a Linux environment, the extension information we are pulling from the WireServer is of the host Windows virtual machine. And here you can see that our host virtual machine has the DSMS for Windows extension, which also has a protected settings section. And as I stated before, the protected settings are encrypted, and we suspect it might contain some sensitive information. So we decided to try and decrypt it. Let's see how the agent itself decrypts the protected settings section. Where does the agent get the decryption key from? Well, similar to the extension configuration endpoint, there is a certificates endpoint for retrieving both encryption and decryption keys. This endpoint also can be found in the machine's gold state we fetched earlier. These certificates are the golden key used to decrypt all sensitive protected settings, making them inherently sensitive information. You wouldn't transfer them in unencrypted communication, right? The way the agent protects these secrets while still using HTTP is by encrypting them, using a self-signed certificate it generates and supplies. The certificate is not validated by the server, meaning we can generate our own self-signed certificate and retrieve the encryption keys from the certificate endpoint. We can do that without relying on the certificates that the agent initially generated. The self-signed certificate is supplied in the XMS guest agent public X509 cert, which is a mouthful of a header. And here's the CRL command with that notorious header that can be used in order to retrieve the keys required for decryption from the certificate endpoint. Here's the response we get back from the WireServer in our test Linux machine. And now, let's execute the same CRL command on the Cosmos DB Jupyter Notebook container. And here's our response. But wait, there is a subtle difference. Can you spot it? The format is different. On our test Linux virtual machine, we got back an encrypted PKCS7 blob, which we decrypted using a handful of OpenSSL commands. But executing the same OpenSSL commands on the CertificatesBondPackage format got us nothing. So what is the CertificatesBondPackage format anyways? The first thing we did, researching the CertificatesBondPackage format, is to consult Google, which didn't have any answers. And then we thought, maybe someone at Microsoft will have the answer, so we consulted Bing, which didn't have any answer either. Then we thought, the WA agent is the client of the WireServer. It must have some kind of reference to this mysterious format, right? Well, wrong. 0 references. Then we remembered that according to the metadata service, even though we are running inside a Linux container, our host virtual machine is a Windows virtual machine. Meaning, all the responses from the WireServer are meant to be treated by the Windows agent, not the Linux one. Unlike the WA agent, the Windows Virtual Machine agent, also known as the Windows Azure Guest agent, is not open source. But fortunately, this agent is written in C#, meaning it can be decompiled to something that resembles source code fairly easily. This can be done using a variety of decompilers. We chose ILSpy. And finally, here's the first reference we've seen to the CertificatesBondPackage format, along with its handling code. Shown on screen is a small script we wrote to mimic the agent's CertificatesBondPackage decoding. Now, after decoding and decrypting the CertificatesBondPackage, we expect to get 2 keys, a private key and a public key, used to encrypt and decrypt the protected settings. You can imagine our reaction when in reality we got back 25 certificates and their corresponding private keys, some with very intriguing names. Keep in mind these 3, as we'll encounter them later on our journey. It is also worth mentioning that one of the certificates and private key we got is for the *notebook Cosmos Azure Com domain. This alone already lets us to intercept encrypted SSL traffic of customers' Jupyter notebooks. This is a signed certificate by Microsoft that we have the private key for, after the WireServer simply dumped it on us. At this point, we know we're onto something. So we got a bunch of certificates that we probably shouldn't have, which made us wonder, what's the legitimate purpose for these certificates? So we chose to have another look at the extension configuration we pulled back from the WireServer. Shown on screen is one of the entries of the extension configuration settings we got from the WireServer, specifically the Service Fabric node extension, which had some interesting information in its public settings. As you can see, there is an entry called cluster endpoint, which contains some kind of URL, and there is another entry that mentions a certificate that we happen to have, the Fabric REST US1 certificate. After accessing the cluster endpoint via Google Chrome, an authentication popped up requesting for an authentication certificate. Our best bet was to supply the certificate mentioned in the extension configuration, the Fabric REST US1 certificate we obtained from the WireServer. At this point, we had our fingers crossed, and bam! What we got back is a huge XML file containing a bunch of cluster information. Let's highlight some interesting points. First, there is another reference to the Fabric REST US1 certificate, which made us believe that this certificate does have some kind of significance in the context of our cluster. And there is a reference to an HTTPS port at port number 19080. And another reference to that strange keyword, Service Fabric. What is Service Fabric? At this point, we had no idea what Service Fabric actually is, so we Googled it. Then we encountered this MSDN article. As you can see, according to MSDN, Service Fabric is a container orchestration solution. But from this point until the end of our research, we treated it as Kubernetes. Although this is not the perfect comparison, it was good enough for our purposes. The manifest files mentions port 19080, which according to documentation is a Service Fabric management port. The manifest files also mentions a few IP addresses in the 10.0.0.0/16 subnet. And according to the instance metadata service we've accessed earlier, our machine is inside the 10.0.0 subnet. And after flashing the IP table rules, we can access other endpoints inside of our subnet. A port scan showed that some of the endpoints in our subnet are listening on port 19080, the Service Fabric management port. We can use the Service Fabric Linux command line tool, sfcmtl, and try to connect to the management port. The authentication process requires a certificate. And there seems to be that one certificate that seems to have all the answers, the Fabric REST US1 certificate. So let's try it. Here are the two commands used to authenticate and list all the application instances in our cluster. We issued the last command and wondered, will it work? Well, it worked. The application list command yielded more than 500 Cosmos DB instances in our regional cluster, and for each instance, we received a bunch of encrypted authentication tokens. But as I said, all of these authentication tokens are encrypted. They are useless for us. No endpoint will receive my encrypted authentication token. But wait, to this point, we only used a fraction of the certificates we've obtained from the WireServer. So maybe one of these certificates are the ones used to encrypt the authentication tokens? After brute forcing the certificates, we felt dumb, now knowing that the encryption certificate had a pretty indicative name. The Fabric Secrets was the one certificate used to encrypt all customer authentication tokens in our cluster. Just one certificate to encrypt all cross-tenant sensitive authentication tokens. Decrypting the Cosmos DB account key resulted in us gaining the primary key for all Cosmos DB accounts in our cluster. This primary key is equivalent to the root password to the database, allowing full access and manipulation of the victim's data. I will now hand over the presentation to Sagi to demonstrate you the complete exploit chain.
Thank you, Nir. Unfortunately, we cannot show you a live demo of the exploit because this vulnerability is now patched, but luckily we were smart enough in order to record one in advance. So let's view it. So as you can see, the screen is now splitted into two parts. The right part is our research account, which we will perform the attack from. And the left part is the target Cosmos DB account that we want to take over. As you can see, the two accounts do not belong into the same organization, and we will also inspect the access control rules to make sure that the research account does not have any special privileges over the target account. The next thing that we'll do is to set up a Jupyter Notebook container and jailbreak it. So as we are already running with root privileges, all we have to do is to flush the iptable rules by issuing the iptables-f command. After flushing the iptable rules, we can now execute our exploit script. Now, you can see that our exploit scripts requires the name of the account that we want to take over as a parameter. I want to emphasize that this is not a requirement by the vulnerability. This is actually just a precaution that we took while developing this exploit to make sure that we do not access any data that is not our own, even by mistake. After executing the exploit script, you can see that it dumped on us the plaintext version of the Cosmos DB account key, and if we compare it to the primary key that you can find in the management panel, you can see that they are identical. So let's quickly recap everything that happens behind the scene in this video. First, we set up a Jupyter Notebook container for our Cosmos DB account. Then we obtain root privileges inside the notebook container and jailbreak it to be able to access network resources. Then we query the WireServer for certificates and extract the cluster manifest from the extension config. Then we use the certificates from the WireServer to connect to our local service fabric cluster and dump the encrypted credentials of all Cosmos DB accounts in that cluster. Finally, we decrypt the secrets using another certificate we obtained from the WireServer, the Fabric Secret Certificate. You would think that would be done by now, but we didn't stop here. We only used a fraction of the information that we obtained from the WireServer. Let's see what else we can find. Let's have another look at the extension config and the cluster manifest. This is a snippet from the cluster manifest, and as you can see, we have a couple of connection strings here for some Azure storage accounts. But unfortunately, these connection strings still require a key. Luckily, these keys can be found in the protected settings section of the extension in the extension config. And these are the commands that we use in order to decrypt the protected settings. And as you can see, this is the plaintext key. So we now have 4 connection strings to different Azure storage accounts, and these are the accounts. It is only reasonable to try and explore them using Azure Storage Explorer. This is what the Azure Storage Explorer interface looks like when you connect using our connection strings. Generally, this bucket contained hundreds of gigabytes of data in them, but the most interesting thing that we found was a log file that indicated that the IP addresses in the 10.0.0/16 subnet may have an external interface, a public IP address that can be accessed from the internet. We thought, this might be reasonable. Perhaps Microsoft had the reasons for it. But in any case, this IP address must be allow listed, right? I mean, there should be absolutely no reason at all that we will be able to access it from our office, right? Well, wrong. Turns out that we were able to access to this IP address from our office over the internet and view the control panel of the underlying service fabric. This is what it looks like. Just to make sure we all understand, this is some internal Azure infrastructure that we can access from the internet. At this point we were thinking, this can be the only endpoint that is accessible from the internet. There must be more endpoints like this. So we decided to scan the internet for the service fabric management port and see how many endpoints will let us authenticate using our master key certificate, the fabric.westus1 certificate. We managed to successfully authenticate to over 100 service fabrics from our office over the internet. Even though we use the fabric.westus1 certificate, turns out that it can be used to authenticate to many other regions and services. Here's a sample of the service fabrics that we successfully authenticated to over the internet. At this point, we suspect that service fabric is a core component inside Azure and is used to do a lot of things behind the scenes. I will now hand it over back to Nir to summarize our findings.
Thank you, Sagi. Let's talk about what we found and what is the impact. We managed to retrieve multiple secrets that allows us to access and manipulate customer data in multiple access vectors. The first secret is the Cosmos DB account key, which after decryption is identical to the primary key of the Cosmos DB account. As you can see, this is the key from our exploit output, which is identical to the primary key found in the management panel. This key is equivalent to the root password for the database. Another authentication token that we have is the notebook auth token. This token can be used in order to execute arbitrary code inside the Jupyter Notebook container. After executing code there, we can use this access to extract the database secrets. In this picture, you can see how we executed the ID command in our container using that token. The last token that we'll talk about is the notebook storage account key. This token can be used in order to manipulate the content of existing saved notebooks, potentially making the victim execute malicious queries on their database without even knowing. We confirmed that all of these tokens can be used to access the databases of thousands of Azure customers, including numerous Fortune 500 companies. Along the way, we also obtained a Microsoft signed certificate that can be used to intercept SSL traffic to the notebook service. And we also retrieved connection strings to the Azure storage account that reveal metadata regarding customers' environments. Overall, we believe that we proved a high degree of control over the entire service, especially when this access can be maintained without accessing the vulnerable environment, but instead from the internet. Let's talk about the disclosure timeline and our work with Microsoft. On August 9th, we first managed to exploit the vulnerability. And 3 days later, we already sent the advisory to Microsoft. We understood that this is a very severe vulnerability, and we wanted to let Microsoft know as soon as possible. 2 days later, we noticed that Microsoft has mitigated the issue. The way Microsoft chose to address this issue is by removing the Jupyter Notebook feature altogether. This is an extremely fast patch. Only 48 hours after our report, the feature was disabled to all Cosmos DB account customers. On August 16th, we first heard back from Microsoft confirming our findings. On the same day, we started seeing that some of the credentials we obtained during our research are starting to be revoked. And the next day, Microsoft awarded us with the maximum bounty available for Azure, $40,000, which we plan to donate. This is the fastest bounty we've ever seen from Microsoft, only 5 days after our initial report, which was on a Friday. On August 23rd, we had a great Teams meeting with the Microsoft team where we discussed their mitigations, and they confirmed to us that there are several thousands of customers that are impacted by this vulnerability. And 3 days later, Microsoft sent an email notifications to Cosmos DB customers that had the Jupyter Notebook feature enabled during a research period. But we think that Microsoft should have emailed all potentially impacted customers. Although that this vulnerability is now patched, you can never be sure that this vulnerability wasn't exploited prior to our engagement. So here's a TLDR of our entire engagement before we finish. We jailbreak the notebook container that comes bundled in with our Cosmos DB instance by exploiting bug number 1 and bug number 2. Then we contacted the host machine WireServer and got back 25 private keys which we only used a small portion of. We used a couple of these private keys to connect to our regional service fabric control panel and listed the Cosmos DB instances in the clusters, including their credentials. Then we proceed to use the same certificates to connect to other Cosmos-related service fabrics management panels over the internet. After a week of research, we had to stop our engagement and reported everything that we found to Microsoft. All in all, we think that this is as close as it gets to a service takeover. So yeah, this is the story of ChaosDB, the vulnerability that allowed us to hack the databases of thousands of Azure customers. Thank you.